afternoon, everyone. So I am Himan Malik. I'm an assistant professor in the Department of Electrical Engineering. So welcome you all to this INUP User Awareness Workshop. So today I am going to talk about this reactive ion etching and wet etching process, which is largely utilized in many of this micro and nano fabrication processes. Before going to that, just in electrical engineering department, my group is called Interdisciplinary Microsystems Lab. So we work on different type of microsystem, that is different type of MEMS and MEMS devices. So this is just a brief overview of the different activity that is going on in my research group. Before going into the actual etching process, so from my own research perspective, if I try to explain like why this etching in general is important. So if you see different type of MEMS and NEMS devices, so we are all familiar with this kind of MEMS accelerometer or mass sensor, different kind of sensors, then this micromirror or energy harvester, this kind of devices. So what we see there is that they are quite three-dimensional in nature, basically. So you have some sort of a silicon structure. On top of that, you might have some kind of a metal, some other materials. But this is a three-dimensional structure, means it has the underlying the silicon layer. So if you consider this particular example for this case, that there is a hollow or a vacuum or a hollow space on bottom of this silicon layer. So this allows this structure to move freely on when it goes a motion, kind of out of plane motion. Now the question is how this hollow space is created out of this solid substrate. So this kind of spaces actually you can see in many of these devices. Actually, in all of these devices are available, and this is not just true for this kind of MEMS or NEMS devices. This is true for many other devices also. So this kind of hollow structure or the subtraction of material or removal of material from the substrate is typically done using this process, which is called the etching, right? So today I'm going to talk briefly about this different etching processes, and then what is the facility that we have in our NRF that I will go through. But before explaining the different etching processes, it is important to know few basic consideration about this etching processes. So first of all, there's etching or subtraction of material from a substrate can be of two types, mainly depending on the etching medium. So if the etching medium is liquid, it's a wet etching process, or if the etching medium is vapor or gases, then it's a dry etching process. Now this dry etching process can also become in a couple of ways. So it can be physical, where like some ionized particle which have a very high momentum imparts on the substrate surface and take off some of this material. So that's a physical process. There is nothing chemical reaction happening or anything. So that's a totally a physical kind of process. You can compare this with the sputtering process that you probably studied in today's morning, one of this today's morning lecture. So that type of etching is also called the ion milling process. Now this dry etching can also happen in the chemical reaction mode. So then it's a chemical process. So then the thing is that, so you have this chemically reactive ions which are created on some plasma medium. So they again come in contact with the substrate surface, and then they do some chemical reaction with the substrate surface and take off some of the substrate material. So that's a chemical reaction based etching process. Then there can be a combination of physical and chemical reaction based etching. So that's what we call the reactive ion etching. So here you have a momentum transfer also, as well as some sort of a chemical reaction on the substrate surface. Now this dry etching or wet etching, which can be like either physical, chemical, or a combination of this physical and chemical modes, can be divided again into two types. So depending on the nature of the etching. So they can be isotropic etching, and that can be anisotropic etching. So what is meant by isotropic etching? Isotropic etching is if in a substrate So when you try to do this etching, basically you have a substrate and you have a mask layer. So mask layer actually is defined by the lithography process. Now this mask layer, what it does, it opens up a particular portion of the substrate where you want to etch, or from where you want to remove the material, right? So now if this etching is happening in all directions in a simultaneously in equal speed or in a uniformly in all direction, then what you get a uniform etching throughout all directions, and that type of etching is called the isotropic etching. So if you see that, so here you wanted to etch actually in the vertical direction, but because of the isotropic nature of the etching has happened in all directions simultaneously. So an important case in case of this isotropic etch is the undercut. So you get a lot of undercut in case of a isotropic etching. And that is actually a problem. We can say that for isotropic etching, because ultimately we want to have this etching in the vertical direction only. But that can be achieved using anisotropic etching. So in case of anisotropic etching, what happens? So you get a directional etching. So you have the mask layer, you have the substrate, and your agent actually etch in the one particular direction. So in this case, this is this vertical direction. And so you get your undercutting is actually very minimal. So you obviously get a little amount of undercutting, but that is not significant when you compare it with the etching that is happening in the vertical direction. So based on that, so this isotropic and anisotropic etching, there are a couple of terms also that is important for any etching analysis. So first of all, what is etching rate? So etching rate is the etching depth divided by the etching time. So in this case, the etching depth is actually the etching in the intended direction. In this case, the etching is intended in the vertical direction. So etching depth will be in this case D. So this etching rate is given by etching depth divided by the etching time. And then second thing is the degree of anisotropy, which defines how much undercut you are having basically. So degree of anisotropy is defined as by this formula 1 minus RL by RB, where RL is the lateral edge rate and RB is the vertical edge rate. So basically, if your lateral edge is very small, that is you are getting quite an anisotropic etching, then this RL will be very small and your degree of anisotropy will also become kind of close to 1. So more it close to 1, ideally if it is actually 1, then you get a perfectly ideal anisotropy, but in practical process that is not possible. So the more it goes towards 1, basically your degree of anisotropy is better. So in case of anisotropic etching, the U is much less than D. So U is the lateral edge dimension and D is the vertical edge dimension. So if U is much less than D, then A is almost equal 1. And for isotropic etching, because of its isotropic nature, U is almost equal to D. So in this case, A is almost equal to 0. So the degree of anisotropy in case of an isotropic etching is close to 0. The other term that is very important in case of etching is called the selectivity. So selectivity is given by the etch rate of the etch material and etch rate divided by the etch rate of the mask material. So this mask is utilized to protect your certain part of the substrate and to open up a particular portion where you want to etch. Now if your etchant actually start etching this mask layer also, so then after a point what will happen, this mask will completely get etched off and your this substrate will also open up underlying the mask. So that time the entire purpose of selective etching is going to be ruined. So this selectivity is also a very important term when you are considering this etching process. Okay, so when we talk about wet etching, so wet etching is isotropic in nature. So in wet etching, it's a liquid-based etching. So there you have some wet etchants like some particular mixture of acids or reactants. So that's actually chemically react with your silicon substrate or silicon dioxide or any other substrate. And then as a result of this chemical reaction, basically they start etching in different directions. So in case of silicon, its isotropic agent is HNA. So that is a combination of hydrofluoric acid, nitric acid, and acetic acid. So in similar way, your silicon dioxide have the agent of buffered HF or HF vapor. Silicon nitride has a agent of hot phosphoric acid. And polysilicon has the agent of KOH. The silicon can also have anisotropic agent like KOH, EDP, TMH, etc. So before going into this weight etching, so it is important also to go through the silicon crystallography little bit. So we know that the silicon substrate surface is a 100 plane. So based on that, the 110 plane and 11 planes are shown here. Now it is important to know that this silicon crystal do not have the similar kind of crystallographic structure in all these planes. So some planes are softer, some planes are harder, and how this softness or hardness is defined is by their crystallographic arrangement, how the atoms are arranged in this particular plane. So if we see the crystallographic or atom arrangement in the 100 plane, so they are arranged in a quite like a periodic manner, in a uniform manner. So that's why their property, when we see their mechanical or chemical property, so the chemical how they react to different kind of chemical reaction is a very they react very easily to this chemical reaction. So that's why they are also very soft. On the other hand, if we see, for example, the atom arrangement in 111 plane, so in that case, the atoms are placed, if you see from the 111 plane view, then the atoms are arrangement in quite a kind of dense manner. So that's why they are also chemically not very active in this plane. And any chemical agent that is trying to react with this plane and etch off the material, it's not so quick or not so easily that is happening. So that's why this 111 plane, it's kind of very hard, and the 100 plane, on the other hand, due to its crystallographic orientation, it's kind of soft. So that's when you try to etch silicon, so what happens is the etch rate in the 111 plane is actually quite high when it's compared with this 100 plane or 110 plane. Now, this actually creates a mismatch of etch rate in the different plane. So when you start etching silicon, so your 100 plane, which is the top surface plane, it will happen very quickly. And when it comes down to when it's etching continuously and comes down to this 111 plane particularly, the etching rate is kind of minimized. It becomes very small. So at that time, the etching kind of stops. And so ultimately, what you get a etching profile like this. So this is again a 100 plane. So when you see that, when you are etching or doing weight etching from the top surface, it's etching. And ultimately, when it comes to this 111 plane, so the etching stops, and so you kind of get this kind of a tapered kind of profile due to the etching. So this is the anisotropic etching of silicon, and the different dimensions, like the top opening of the etching portion to this lower side of the tapered etching profile. All this has a particular dimensional relations, which is given by this equation. So from that, you can actually estimate like what will be your mask opening to achieve a particular etching profile in one particular case. So if you want to do anisotropic etching, so there are few popular anisotropic etching of silicon. So starting with the potassium hydroxide, so this has a very high etch rate and anisotropic, but they are also very aggressive in nature. So these are very aggressive agent. So that's why their etch rate is also high. But the problem is that it is very difficult to find a proper etching mask for this KOH agent sometimes. Only a material which is very uniform and without any kind of hole, So that kind of material can be used as a etching mask for this KOH. So LPCVD grown nitride are a very good example of that kind of etching mask for KOH etching, because these LPCVD grown nitrides are typically very uniform without any kind of pinhole or anything that doesn't allow the reactants or solution to go inside the inside the mask layer basically. Then EDP is the other agent, so that is also a very high etch rate, but they are not typically preferred because of their toxic nature, and also they degrade quite quickly. The third one is the trimethyl ammonium hydroxide. So that is sometimes very quite highly preferred for this this kind of silicon wet etching because of their high anisotropy when compared with the EDP, but at the same time they are not as aggressive as KOH, so their etch rate is kind of slower than this KOH etching. Now, when you are doing the wet etching, one of the major consideration is that what is going to be your edge stop. So one of the good way of defining this edge stop is through the crystallographic plane. So we saw that in different direction of the silicon crystallographic plane, the edge rays is defined. So if we now define our mask opening in such a way that when it etches down to a particular depth, the etching actually stops. So then that is the best case, because ultimately when you etch this, if you etch it further, at some point what will happen, these two tapered lines will actually join and they will form a kind of like a triangle, and then the etch rate will stop. So then that is the etch stop by using a crystallographic plane. So that is a very good way of doing that, but in that way you get a particular kind of a profile or particular kind of a shape in case of the silicon substrate. So like here, so you get a particular triangular kind of shape with the crystallographic edge stop. The other way of doing the edge stop is through having a highly doped silicon. So if you have a highly doped silicon, then basically you are actually increasing the concentration of atoms within the substrate, and then the chemical reaction also kind of like slows down and stop at a particular distance. So that is another way of doing that. The third way of doing that is using a electrochemical edge stop method, but I am not going into the details of that. That requires a particular setup, and that is not very straightforward. But our main discussion today is regarding the dry etching process. So chemical wet etching is obviously can be isotropic and anisotropic, but the degree of anisotropy, if we consider in case of wet etching, it is still not that much, and also the etch rate is kind of limited. So in order to address those two challenges, that the dry etching is more popular. So dry etching happens inside a chamber. So where you control the process pressure basically, and this process pressure can be classified into 3 different regions. So if one region is quite high pressure, so that is the region where your plasma etching is happening. The other region is on the other end of this like graph, so which is the quite low pressure region where this ion milling is happening, or which is also kind of the physical mechanism. Plasma etching is kind of the chemical mechanism, and in between that, in a mid pressure region, we can say, where we can combine both this chemical etching as well as this physical etching, and we can have this reactive ion etching basically. So before going into again this reactive ion etching, I am just going to talk about this one type of plasma etching. So that is like one type of dry etching, that is the plasma etching. So this is a typically like a plasma etching process where like you use a different plasma or vapor to remove certain material, like this xenon difluoride vapor is used for etching of silicon, or HF vapor is used for etching of silicon oxide. So this is a typical setup where you have an etching chamber, you put some use some like vapor, so that is inserted using some chemical reaction, and through then expansion chamber you insert that vapor into the process chamber, and on that process chamber there this chemically reactive ions using some like plasma, so they come on top of the substrate surface, and then they undergo some sort of a chemical reaction and etch out the material from the substrate surface. So this is a chemical way of doing things. Now, if we have considered, our main consider is the reactive ion etching. So reactive ion etching, what's happened? So this is a typical setup of a reactive ion etching chamber. So here what we have, you have a chamber, on inside that you have a bottom electrode. So you have two electrodes basically. So if you consider this as a bottom electrode, so that is connected to some radio frequency, like a radio frequency source of potential, electromagnetic source of potential. So that is connected to the bottom electrode, and there is then a top electrode also, and that is along with that the chamber surface that is completely grounded. You have certain gas inlets, and then like what happens? So it is kind of a like a creating a RF plasma inside the chamber. So like you are applying this RF source to the bottom electrode, and your top electrode is grounded. So it's acting kind of like a capacitive mechanism. So this is inside this chamber, what is happening? You are creating this RF plasma, and when you are inserting this gas inside the chamber, so this gas is basically ionizing, and this ionized gas creating some free electrons as well as the positively charged ions. So these ions typically, first of all, because of this this ions, they are heavy compared to this electrons, and then because your substrate is placed on top of this bottom electrode where you apply this potential, basically these ions that is created here inside the plasma, they are bombarded. So they are transferred to the substrate using this momentum transfer, which is the physical mechanism side of the process. Now, once they are bombarded onto the wafer surface, they undergo chemical reaction and creates this byproducts, which are removed from the chamber using this exhaust lines. So then there are two type of mechanism. First, this plasma is created, and then the plasma is created by the gas that is like inserted into the chamber through this inlet lines. This creates this positively charged ions, and these ions are bombarded onto the wafer surface. So that is a momentum transfer process. So that is a physical mechanism. Now, once they are bombarded onto the substrate surface, they undergo this chemical reaction. So that is the chemical side of the process. So in combination of these two, they are kind of like etching of the substrate material, and the byproduct that is produced are removed from the chamber using this exhaust lines. So this is the basic mechanism. Now this reactive ion etching or happens actually at a process pressure which is intermediate between your chemical process and your physical process. So in chemical process, that is happening at a quite high pressure basically. So then what's happening there? So if I go back to this one, so this kind of like creates a trade-off between the physical process and the chemical process, right? So what is happening? The mean free path in case of when the pressure is low, that is in case of the ion milling process, the mean free path for this ion transfer is actually quite long. So the ions actually get transferred to the wafer surface without any kind of collision or very less amount of collision. So then their momentum transfer is quite direct, and the momentum transfer is quite high in nature. Whereas in case of plasma etching, this momentum transfer is not that important. There the chemical reaction is mainly important. So there the mean free path is quite low actually. So because this reactive ion etching is a combination of both, so here you follow an intermediate path. So here the process pressure is also affecting this main free path. So the main free path is not as large as a ion milling process. So the momentum transfer is not as much as in case of an ion milling process. But on the other hand, it has the plus point of this plasma etching, that is the chemical reaction. So in chemical reaction, so the momentum transfer is also happening, as well as the transferred ions are also participating in some kind of a chemical reaction. So that based on that, the this like the etching process is happening. So now the only the thing with this reactive ion etching is that here you are creating this plasma based on a capacitive mechanism, right? So you have this two electrodes that is creating this plasma, as well as this the potential or the electric field that is being created here between these two electrodes are also forcing these ions to bombard onto the substrate. So these two mechanisms are directly related to this capacitive mechanism between the two electrodes. Now, if we can decouple these two mechanisms, then what we can do, we can increase the etching rate as well as the anisotropy. So that can happen using a slightly different version of this RIE, which is called the inductively coupled RIE or inductively coupled plasma RIE, that is ICP-RIE. So here, what is the difference between a standard RIE and the ICP-RIE? Here we just decouple the mechanism of this plasma generation and this like directionalizing the ions that is created inside the chamber to the wafer surface. So here what you get, here we have some kind of coil around the chamber, and you apply this the ICP power onto this coil so that circulating current is generated, and this current creates a magnetic field inside the chamber. So this plasma is actually created based on this magnetic field. So that is why it is called the inductively coupled plasma. And along with that, there you also have this on below of that substrate, you have this electrode also. So that is that electrode basically creates the electric field that is responsible for movement of the ions towards this substrate. The substrate is placed on top of this electrode. So the ions that is created due to this plasma are actually directionalized because of this potential that is applied to the bottom electrode. Now, as you decouple this plasma creation mechanism with the flow of the ions towards the substrate, so two things happen. So you can create a very high amount of plasma so that you can increase the plasma density. So a lot of so your basically the more and more ions are created, and then it can happen at a lower pressure basically. So that has a significant benefit also. So the combined effect of this decoupling of this plasma creation and directionalizing this ions is that you can increase the anisotropy. So you can understand that because now you have a very high plasma density, so your more ions are created and they are quite highly directionalized because you have a different mechanism for directionalized towards the substrate here, those ions. So what is happening here, that you get a lot of high anisotropy, and because of this high anisotropy, you can create a highly high aspect ratio structures onto the wafer using this kind of a inductively coupled plasma RIE technique. The next process that is quite utilized in many device fabrication, particularly in this MEMS area, is called the deep reactive ion etching. Though this is slightly a different thing, but I will just like to go through this process briefly. So this is just another version of the reactive ion etching with a deep term. So that is a deep reactive ion etching. It is also called a Bosch process because it's of the person or the company that patented this process. So that's the Robert Bosch company patented this process. So based on that, it is called the Bosch process. So here, what's happening here? It's a kind of like a time multiplexing etching process. So here you have a etchant as well as a passivating kind of gas that is passed onto the chamber. So the etching gas, what it does, it etches the surface, but the passivating gas, what it does is that the passivate the etched layer slightly for the directional. So let me explain from this figure. So the process can be divided into 3 steps. So in the first step, what is happening? You are passing the etching gas. Say in this case, sulfur hexafluoride is the etchant for silicon. So you are passing that gas. So it's etching directionally towards the surface and etching the substrate. Now, when the etching step is complete, you have a passivation step. So in the passivation step, tetracarbon octafluoride gas is passed. So it's basically what it does. It passivates the side walls as well as the bottom layer. So passivation means it's kind of creates a layer of polymer around the surface that is being created. So in next time, when the passivation time is over and a next etching cycle is started, what's happening then is the SF6 gas, what it does is it's again bombarding onto this open surface now, but now it can't really has that momentum to remove the polymer layer that is being created onto the side walls. So it can't really etch the side walls anymore, but it has the enough momentum to etch off the bottom or the bottom layer that is created here. So it's etched quite in the directionally onto the and anisotropically into the substrate. So as a result of that, if we now can continue this etch and passivation step one after another with time, what's going to happen is that we will get quite a directional structure. So we will create a very high aspect ratio structure, and that is quite directional in nature. So that is the utility of deep reactive ion etching. And in typically many devices in MEMS and other things where you need to etch the bulk silicon or the substrate layer to a very substantial thickness, say 400 or 500 micron thickness, then this kind of deep reactive ion etching process is utilized in that case. So using this shows some of the process result for Bosch etching or deep reactive ion etching process. So you get almost like a 90-degree side walls within this kind of deep reactive ion etching process. And these are quite high aspect ratio in nature. High aspect ratio means your top surface layer can be very small, but your Z direction etching is very high in nature. But there is something to be careful of in this kind of DRIE method also. So if you now take a very zoom look at these side walls, what we can see is that it's not actually very uniform. Rather, there are very small size this kind of structure or this wavy structures, which is called the scallops that are created. So why it is created? So we said that in case of a DRIE, we have this passivation step where you passivate the side walls using some sort of a polymer. Now, when the next step of etching is happening, so they are obviously unable to etch the side walls significantly, but still there is some minimum amount of etching is going on. So because of that, this kind of scallops layers are created in multiple cycles of this DRIE process. But that can be actually optimized and minimized by optimizing different process parameters. The other thing about this Bosch process or the DRIE process is that, as I was saying, that you can create a very high aspect ratio structure using this kind of process. So you can have a very large opening with a very large depth also, or very small opening with a like a comparable depth also. but it is preferable that in a same process, your openings, the mask openings should be almost around the similar size scale. Otherwise, what will happen is that in the etching step, the large area of etching openings will get more etched, and the small area of etching openings will get smaller etching. So as a result, when you etch for a longer duration of time, you will see that the etching depth are not uniform across all the opening of the etching layers. So that is a problem that we must face. So the solution to this problem is that we need to design our mask in a certain way to eliminate these large disparities in the opening. In that way, this discrepancy in the different depth of the etching can be avoided. Okay, so in our NRF at IIT Delhi, we have this reactive ion etching setup. So that is mainly is utilized for etching of different semiconducting materials, particularly silicon, silicon dioxide, etc. So the kind of etching gases that we have are carbon tetrafluoride, fluorofluorine, sulfur hexafluoride, argon and oxygen, etc. So we use it for multiple purposes, and we use a substrate of different size, like up to 10-inch or smaller pieces. We utilize. So if you think that in your device, like this RIE can be useful for some etching step, then maybe later on when you want to like proceed with some sort of a project mode where you will be thinking of fabricating some particular device using the facilities here, you may think of utilize that, but you need to take care of take into consideration some of the things before you actually utilize this particular setup, like what kind of etching gases are available, so they will be suitable for what kind of material. So typically we etch here silicon, silicon dioxide, etc. And the substrate size is also kind of limited. And application wise, it is mainly utilized for different semiconductor device purpose, also for different MEMS and MEMS device purpose, solar cell, photonics, optics, etc. And it can be utilized for different applications also, like prototyping, different kind of, if you want to have your analyze different like structure or device for different R&D applications or failure analysis, etc. So you can utilize this reactive ion etching setup here. So these are some of the etching profile in silicon that has been done recently here. So the etching profiles are shown here. So by optimizing the different etching parameters, our students have been able to etch up to a very large depth, up to almost 80 to 100 micron, as well as the side profiles also are not that bad. So they are quite anisotropic in nature. But obviously these processes can be further optimized according to the requirement. So that is a different thing. But this is kind of the facility that we have right now. So I hope that you get a flavor of different etching processes, particularly this reactive ion etching process. So